Nos queda un ponente, tenemos el tercer ponente de hoy, es Dame Jocelyn Bell. Jocelyn Bell es astrofísica, probablemente su trabajo más conocido sea el descubrimiento de los púlsares, o las estrellas de neutrones que emiten radiación de forma periódica, y por el que le dieron el premio Nobel a su director de tesis, Anthony Hewish. Jocelyn Bell es profesora en la Universidad de Oxford, es también presidenta de la Royal Society de Edimburgo, en Escocia, y bueno, hemos escuchado primero a Tadley Herzog y su visión entusiasta de la ciencia y de intentar alcanzar lo imposible. Hemos visto una visión distinta a la de las máquinas que aprenden a ver. Yo creo que la visión de Jocelyn Bell ahora es también distinta y responde a uno de los instintos quizá más primarios de la curiosidad intelectual, que es mirar hacia arriba, mirar los cielos y mirar las estrellas y hacerse preguntas pues, sobre lo más grande, sobre el universo. Así que de eso es de lo que nos va a hablar Jocelyn Bell. Then Jocelyn Bell, please.
This side. Oh, right. It's right here. Thank you. Good evening, ladies and gentlemen. Thank you for the opportunity to be here in this wonderful place. And thank you for the opportunity to be here as part of Passion for Knowledge in this very special year. The two other talks this evening have been very much focused on humans and some of the attributes of humans that machines take. I'm now going to take us to bigger scale and out into space, to the universe. Perhaps you've seen pictures like this. It's an image from the Hubble Space Telescope, a very special image. It took a long time to make. To see so deep into space, the deepest we have ever seen, the Hubble telescope had to stare for 143 hours. It's looking at a very small area, the area covered by a tennis ball at 100 meters. And there are many interesting things in this picture. We are seeing objects that are 12 million light years away. The universe is only 14 million years old, so we're seeing a long way back. We are seeing mostly galaxies. There is one prominent star in the image. It's the one with the cross shape through it. Everything else is a distant galaxy. And one of the other significant things for cosmologists is that there is black, empty space between the galaxies. But there are some disadvantages in staring deep like that for very long. We are looking at a small area, and we get interesting results, but because we do one long stare with one image at the end, we miss things. We miss things that are of short length, short duration, flares. We also, incidentally, miss anything that moves because it has a faint and blurred image. I have an analogy. Suppose you want to photograph some traffic lights. Why do you want to photograph traffic lights? I don't know. But suppose you want to photograph traffic lights. If you make one long exposure, you get the image on the left. You see the red and the amber and the green, all of them half of full brightness. If you want to see the pattern of the lights changing, you must make several shorter exposures. It's a bit like the transition from having still pictures to having moving pictures. You can have a still picture of fireworks, but a video, a movie, is better and shows more of the detail. And it's that transition that we have been making in recent years. Up till now, we have largely ignored the dynamic sky, the sky that varies, the sky that goes flash and bang like fireworks, because we have only had the one deep image. Now, I'm speaking at the moment particularly of optical astronomy, using the light that our eyes can see. We also do astronomy at other wavelengths, and particularly X-ray astronomers and gamma-ray astronomers are well aware that the universe varies a lot. And so too, for the last 50 years, have been people who studied pulsars, because they pulse, they vary. But now, starting with some small telescopes, we've started looking for optical, visible things that change. And the kind of telescopes we've used so far, in the center is one of the old Palomar telescopes in California. Up top right is a Swedish telescope that is actually in Australia. And on the left is a telescope that has recently been built in Hawaii. And these now are all focused on looking for transient events. Sometimes optical images are hard to see. I suspect you cannot see the image up the top. We'll have the lights down a little bit, and maybe that will help. There are 3 images of a galaxy, and just below the center of the galaxy, there is a bright object that is pretty bright in the left hand, weaker in the middle, and a good deal weaker still on the right-hand side. It is a star that has flared in a major way and is dying after the flare. It's actually what we call a supernova, which is a mega death explosion of a star. And in these 3 frames, it has been caught dying. The frames are about a week apart. One of the big changes that has allowed this change in the way we do astronomy, well, 2 changes. One is developments of CCDs, charge-coupled devices, which are in cameras. We have even better, bigger ones for astronomy. And the other major change is developments in computing and the ability to handle large quantities of data rapidly. And those 2 developments, which is really what's allowed the development of this field. And these days, instead of taking a long stare, 143 hours or whatever, we take a frame. We take a frame. We take a frame. We take a frame. You can add up the frames to get the long stare, but because we have lots of different frames, like the frames in a movie, we can see things that change. And one of the big debates at the moment in the field is, how many frames do you take? How long is each frame? What gap is there between the frames? And having done this for a bit, we then go and look at some other bit of the sky. But how frequently do we come back here to this bit? These are topics that are debated very much at the moment, and it really depends what you think you're looking for. But of course, we don't know really what we're looking for, mostly, because we haven't found it yet. So there is debate. The other thing that's extremely important is when you see something, you must tell the world quickly so that other telescopes can all look at that and help gather more data while it's still happening or is in the very recent past. And that development of telling other telescopes and getting them to look at this bit of sky is another technological development of itself. Until fairly recently, we all carried mobile phones, and I have been interviewing a young astronomer, and his phone went, and he said, "Excuse me, it's a flare," and he told the world, and 5 minutes later he put his phone away, and we went on with the interview. Today it is much better automated. There's a real-time transient survey being done with 2 quite small telescopes in Arizona. One is 1.5 meters aperture, something like that. That's small today. And one is even smaller at about 70 centimeters. And they are dedicated to observing the sky night in, night out. They've been running since 2004, and they have seen 3/4 of the sky regularly. And they have found 12,000 transients, optical transients, because they're using light. These events turn out to be typically what we call AGN, active galactic nuclei. These are the cores, the centers of galaxies, where there probably is a massive, supermassive black hole, and occasionally there are flares from such black holes. There's a similar black hole in the center of our galaxy, but it seems to be quiet. It doesn't flare at the moment. But many other galaxies do, and so you pick up these sudden flares from the nucleus of a galaxy. Or supernovae. Supernovae are these catastrophic explosions of massive stars, and they represent a huge brightening of the star. It can shine brighter than its whole galaxy. And then over the next month, 2 months, gradually fades. We've seen lots of those. What we have not so many of is seeing what happens as the explosion happens, as the brightening occurs. We're beginning to catch some of those now, and that is important information. And the other kind of thing we see is stars that we call cataclysmic variables. They vary in brightness, sometimes quite disastrously for the star, a cataclysm. Another one is on Mount Palomar, Southern California. This one's been running since 2008. And as well as finding lots of those things I've talked about, it's also finding some things we've never been seen before. For example, and I don't know what these are, but they are finding sudden brightenings that last a few minutes, and only a few minutes. And the brightening is much, much bigger than any other explosion that we see. They're about 10,000 times the brightness of these massive exploding stars. And what these are, we have not much clue. Of course, there are hypotheses and ideas and arguments, but what they are, there's as yet no agreement. And after a few minutes, it dies away. Maybe we'll get some supporting data from other telescopes someday. We'll see. This telescope is currently shut down for an upgrade. It's going to be called the Zwicky Transient Factory. Zwicky was a Swiss astronomer, emigrated to the USA, a man who was very full of fresh ideas and never published any of them. But this upgraded Zwicky Transient Factory, they're going to find one of these massive explosions every day. So the data rates are going up. I want to say a little bit about what's called microlensing, because this is another temporal phenomenon, things that change with time. Stars have gravity, and because they have gravity, they distort space around them. And because they distort space, a light ray that's coming along gets bent. And a light ray that was not going to hit you can get bent and focus to you. And similarly for a light ray like this. So you can see up here a distant star on the right, in the middle another star that is the lens, and on the left the Earth. And light rays that would normally miss the Earth get bent and come to Earth. So Earth gets more light. The stars are all in motion. So this alignment is temporary. It only lasts perhaps a few days. So if you're observing the star on the right, it's going along at this sort of level, and then suddenly it gets bright for a few days and drops away again. Suppose the star in the foreground has a planet. Do I mean the foreground? Yes, I do mean the foreground. Up top in each of these there are, 1, 2, 3, 4 frames. The yellow dot is the star. The red dot is the planet. And if I can get the cursor to work, and this is, yep, right. You see the rise in brightness. The rise in brightness with the alignment. If the planet is, I'm sorry, I've given you the wrong. The yellow is the distant star. The red is the nearby star, and this little dot is the planet. If there is a planet associated with this red star, then you see the rise due to the star, and then a very short rise due to the planet. If the planet is a long way from the star, you see the rise due to the star, the rise due to the planet. There are several telescopes looking for this kind of microlensing phenomenon, and one in New Zealand called MOA. You'd never have guessed it was in New Zealand, would you? MOA has found some planets that do not seem to have a parent star. They see only this little peak, not the star that goes with it. They have found about 10 examples of planets where there is apparently no parent star. They are orphan planets. We did not expect orphan planets, but they seem to be there. So what happened to the parent? How did they get separated? Why are these planets on their own? We don't know the answers to any of those questions yet. I've been talking so far about things that we see in visible light, like we use with our eyes. But in fact, there's a whole range of other wavelengths. There's a whole family of light. And this diagram aims to give you some feel for that. In the middle here is the little bit that we can see with our eyes. Perhaps you can see it's got the rainbow colors. If you go out the blue side of the rainbow, you come to ultraviolet, then X-rays, then gamma rays. If you go out the red side of the little rainbow, you come to infrared, millimeter, and radio. And stars and galaxies radiate across this whole range. We do astronomy at all these wavelengths today. I should say gravitational waves, which I'll talk about shortly, are not on this spectrum. They're a different spectrum. But I'm going to talk next about gamma rays. There are transient gamma ray events, and the story of their discovery, I think, is a rather interesting story. The Soviet Union, as it then was, and the United States of America signed a test ban treaty, banning nuclear weapon tests in the Earth's atmosphere. The United States felt it had to monitor to be sure that the Soviets were keeping to this treaty. And they knew that a nuclear test in the atmosphere would produce a short burst of gamma rays. So they put up satellites that could detect gamma rays. And they made sure there were several satellites at the same time, so that if this is the Earth down here, and there was a nuclear test there, this satellite would say it was there, and this satellite would say it was there, and they could see where the test was. They found some flashes. They found quite a few flashes. Starting in 1967, they found bursts a bit like this one, where it's all quiet, and then suddenly, for maybe 10 or 20 seconds, there's a bright flash of gamma rays. And they thought, aha. And then they realized that this satellite, instead of saying it was there, was saying it was there. And this satellite, instead of saying it was there, was saying it was there. The flashes were coming from the sky. They were not violations of the test ban treaty. But this was classified work, and it took a long time to get it unclassified, and it wasn't till 1973 that the rest of the world knew about these gamma ray bursts. So what are they? Well, one question to ask is, do they come equally from all over the sky? Or do they come just from the Milky Way, perhaps? They come equally from all over the sky, which could mean one of two things. Either they are very, very distant, so where the Milky Way lies doesn't matter, or they could be much closer than most of the Milky Way, so where the Milky Way lies doesn't matter. Are they very distant? Are they very close? It makes a big difference to how much energy they need to produce. We see these at a rate of about one a day, and whilst the flash is on, it's the brightest thing in the gamma ray sky. We now know that bursts come in two kinds, that there are short bursts, that's this lot, and there are long bursts, with the break at about 2 seconds. And we now have some theories about what produces these. Short gamma ray bursts, the one less than 2 seconds, they're believed to be a pair of neutron stars, like pulsars, which are orbiting each other, which are gradually getting closer and closer together, and finally merge, and probably end up making a black hole, or maybe a very massive neutron star. And somehow, note the hand waving, somehow it produces a very short, flashed, narrow beam. And that's what we see of gamma rays. The long bursts, they're probably possibly due, to an extra big explosion. Not one of the supernovae that I've talked about, but a hypernovae, don't know what a hypernovae is, but it's bigger than a supernova. That much we can say. So it's a hypernova. And the hypernova might be happening when we've got a really, really massive star, which at the end of its life collapses to make a black hole, or maybe a neutron star. And somehow also out of this, there's a narrow blast of gamma rays, which, if it's pointing in our direction, we see as a gamma ray burst. Well, these explanations may be right, maybe not. We will see. Time will tell. But for the moment, hold on to the idea that we've seen gamma ray bursts, some less than 2 seconds long and some more than 2 seconds long. The question of how far away these bursts were got finally settled when, you know, I was talking about somebody's phone ringing. It was a gamma ray burst. The phone rang. He called up some people who worked at ordinary optical telescopes, and they looked at that bit of sky. And there's a pair of photographs here, before and after. These are Spanish photographs. They're from the telescopes in the Canary Islands. And there's a star here that's present on one instance, but is hugely fainter in the second instance. So we think that what has happened is there's a galaxy here, and something in the galaxy has brightened up, but then fades. And so this gamma ray burst is coming from a distant galaxy. The sources of these objects are far away, which is why they look evenly spread over the sky, not very nearby, which was another way they could look evenly spread over the sky. So at least for the long bursts, we have settled that. And they can work out the rate of these things from a few identifications like this, and you get long gamma ray bursts at a rate of a few per galaxy per million years. But there's close to 1 million galaxies in the universe, so the rate is quite high. Another thing that's related to gamma ray bursts is what's called tidal disruption events. And this is where you have a black hole, which you can see, or maybe can't see, here in the middle. And there is a star that's getting too close. And as the star comes closer, it gets pulled into this long shape, an ellipse, and then it gets broken up into several lumps, several bits, which each fall in turn, giving you a sequence of burst, 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 burst. The bursts could be gamma rays or X-rays or radio, depending. But you start looking for bursts due to something falling into a black hole. There's a satellite called SWIFT, and it has found a gamma ray burst that lasts 2 days. The gamma ray burst we were talking about before lasts seconds, less than 2 seconds or more than 2 seconds. This burst lasts 2 days, and we had never seen anything like it before. It's now thought to be one of these tidal disruption events, where a star is falling into a black hole. And the SWIFT satellite has probably now found a second one. But this is all very new. But because we are alert to things brightening up and decaying, we're beginning to find more of these things. This photograph is of a very famous astronomical object. When I was a young grad student, it was said there are 2 kinds of astrophysics: the study of the Crab Nebula and the study of everything else. And we've solved some of the things, but there are still a lot of issues about this particular nebula. There is a pulsar in the middle of it, a famous pulsar, and that explains some of the phenomena. But one of the interesting, maybe embarrassing things is that some of the satellites working in gamma rays have found that the gamma ray signal from this nebula has increased by a factor of 30 for several days, and then finally decayed away again. And to be honest, we have no clue what causes that, except there's a pulsar in the middle, and okay, it's going to take the blame for the moment till we understand better what's going on. I'm now going to switch wavelengths to right the other end of the spectrum, to the radio regime, and talk about some phenomena in radio astronomy. I have to explain to you a phenomenon called dispersion. It's something we have all seen with light, the dispersion of light, because we have seen rainbows, which is caused by dispersion, or artificial rainbows where you shine light through a glass prism. It's not very visible on the screen, but there is a glass prism here. And because the different wavelengths or frequencies of light travel at different speeds through the glass, they get spread out into this spectrum. You can get a similar effect with radio waves, but it's not because you're shining them through glass. As a radio wave goes through space, a lot of space is fairly empty, but there are electrons, some electrons. And these electrons cause the radio wave to be dispersed. And the way it works is that the high frequencies travel faster than the low frequencies. This was first understood in connection with something that amateur radio astronomers were aware of. Amateur radio astronomers were, sorry, not amateur radio astronomers, amateur radio hams. They were aware of something they called a whistler, which sounds a bit like this. And we now know that these whistlers are caused when there is lightning on the other side of the Earth, let's say New Zealand. So there is a thunderstorm in New Zealand, and there is a stroke of lightning, and that produces a radio wave. The radio wave then travels round to Europe, and as it travels round, it goes past electrons, which disperse the radio wave. And what started as with lots of frequencies all at the same time becomes something where the high frequencies come first and then the lower frequencies. So you get, and I have an audio recording of one of these whistlers. Let's see if we can get this bit of technology to work. There is a lot of static, but I think you will hear. Yeah. Right, try again. If there are a lot of electrons, the dispersion is very long. So it goes. If there are very few electrons, it's fast. So you can tell how many electrons there have been by how drawn out the whistle is. Now, I'm going to talk for a moment about pulsars, and there is a connection. Pulsars, our knowledge of pulsars is almost 50 years old. And our understanding of what a pulsar is in cartoon on this slide. There is this very small, very dense star, about 10 kilometers radius, mass of about 10 to the power 27 tons or something like that. Huge density, spinning very, very rapidly about a vertical axis. And it has a strong magnetic field, about 10,000 million times the strength of the magnet on your fridge. You have something on your fridge? It's about 1/100th of a Tesla. These things are about 10 to the power 8 Tesla. So it's a strong magnetic field. We don't know why, we don't know how, but there's a strong magnetic field. And the magnetic field, as on Earth, is inclined. Magnetic north is not at the geographical north. And so as the star spins, this magnetic north pole traces a circle on the sky. And we think that somehow, again with lots of hand waving, from this cone there comes a beam of radio waves. And so as the star spins, there's a beam of radio waves going around the sky like this. And if it happens to shine on the Earth, we see pulse, 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 pulse. Very regular. That's a pulsar, or a pulsating radio star. And they are just like lighthouses. Just as a lighthouse sweeps a beam of light around the horizon, so a pulsar sweeps a radio beam around the sky. And if you observe it with a radio telescope and put on some headphones, you can hear the pulsar. We don't often listen to a radio telescope, but you can do. And this is what it might sound like. That's a star, a pulsar, spinning about 11 times a second. It sounds a bit like a truck or a tractor, a roughly running truck or tractor. Because pulsing at 11 times a second is 660 revs per minute, and the internal combustion engine idles at about 700. So it sounds like the engine in a tractor or a truck. One that needs some maintenance, but that's another story. So how do we know that we're listening to a star and not our neighbor's tractor? The answer is dispersion. Our neighbor's tractor is quite nearby. There are very few electrons between us and it. A pulsar is away out in space, and the signal comes past a lot of electrons. So from this we get, and from this we get. So radio astronomers studying pulsars always check the dispersion. And graphically, would you perhaps look at this lower right panel? It's the clearest. Can you see a signal coming down? No, I should have done it again, sorry. A signal coming down, starting at high frequencies, 1500 megahertz, and about 100 seconds later is at 1350 megahertz. It's descending. And judging by how fast it descends, you can see how many electrons it's come past and get an estimate of the distance. Great. Here's another one. Something that the pulsar astronomers picked up. The line is a little faint. There is a trace coming down like this, like that. And it's a very short, sharp pulse. The interesting thing is, if you put numbers on the axis and work out how slowly this is coming down, it is coming down very slowly. It is a long whistle. It has come past many electrons. Okay, let's work out how far away it is. Let's say it has a dispersion of 100 units. and you start working out, and it's in that direction. You start working out how far it's away. So you start counting electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. I've reached the edge of our galaxy. The electron density now drops because there are very few electrons in space. And I need another 78 units. Well, it's probably in a galaxy of its own out there. So maybe that galaxy has 20 units. But I need another 58. And the density is very, very low. It's kilometers away, light years away. So one of the dramatic and interesting discoveries has been the discovery of what we now call fast radio bursts, FRBs. They come from a place where there has never been a signal before. They come from a place where there is never another signal, except in one case. They come from a place where the optical astronomers can see nothing, the infrared astronomers can see nothing, the X-ray astronomers can see nothing, except for one case. So what is it? Well, astronomers have fertile imaginations. They are very creative, to use the word that's in today. And of course there are theories. I'll talk about that in just a second. We know of 17 or 18 of these bursts now. They are at huge distances, way, way beyond the galaxy. But there was an interesting scare, or side story, from Australia. The big radio telescope in Australia has found many of these objects. And they were a little bit puzzled because they were getting something that was sort of, but not the same. And was it lightning? And was it this? And was it that? This sort of other class, Group B, I'll call them, they then noticed that the Group B bursts tended to occur about lunchtime. And they thought, microwave ovens. There is a canteen on the site. There is a microwave oven. People are not supposed to use the microwave oven when there's observing going on, but people do. I'll just do a cup of coffee. Now, here's a piece of advice you need to observe. If you're using a microwave oven and you stop it by opening the door, the microwaves do not stop immediately. There is a short burst of microwaves. This is not good for radio astronomy, and it's not good for you. So when you use a microwave oven, would you stop it by pushing the stop button, please? So they wondered, were they just seeing their microwave oven? But they are now clear that they can distinguish between microwave oven bursts and fast radio bursts. And we're left with 17 or 18 of these things. And we have very little clue what we are. But somebody says, well, of course, it's a supermassive neutron star, maybe formed around about the time of a gamma ray burst. I mean, let's add two unknowns to this game. It's rotating. And while it's rotating, its centrifugal force will balance the gravity. But gradually it slows. And so gravity wins. And your massive neutron star collapses. And it collapses perhaps to a black hole, and you get a radio burst just as it collapses. Could be. Might not be. We don't know. We haven't enough evidence to go on yet. But this is what happens when you venture into a new domain. You hit lots of intriguing and puzzling things that you cannot easily explain. There are new telescopes coming along, specifically for transient stuff. This is one that is building in Chile, a big telescope There is a person, a white person here, give you the scale. The mirror is about 8.5 meters diameter. And it's specifically designed to look for things that flare and flash. And it's so efficient, it is going to find 1 million every night. Would you like to be the graduate student working on that? Would you like to be one of 1,000 graduate students working on that? They're going to have some intelligent learning neural networks so that the telescope says, okay, there's a flash there. Is there a galaxy there? Yeah, okay, maybe it's a supernova. Send it down that pipeline. No galaxy there? Oh, maybe send it down that pipeline. And sort them a bit so that there will be lots of different pipelines, each with a group of graduate students trying to make sense. It'll be great fun. I'm glad I'm not a graduate student. And there's a very, very big radio telescope building called the Square Kilometre Array. It's going partly in Australia, partly in South Africa. And detection of transient radio events is part of its key projects. And I'm going to finish by talking about something you may have read about in the news earlier this year: gravitational radiation, or gravitational waves. Gravitational waves are ripples in space-time, or ripples of space-time. They travel at the speed of light. If you want more details, they're quadrupole, they're spin-2 particles, and they carry away energy and momentum. So what the heck is all this about? This is a visual aid, not a bottle of water. There's gravity between the bottle and me. Well, actually, between the bottle and all of you as well, but I'll be egocentric for a moment. There's gravity between us two. If I move further away, the gravity gets less. And that change in gravity propagates out through space as a gravitational wave, going at the speed of light and all that. Of course, if we do this, it gets even more interesting, because then there's a regular wave goes out through space, rippling space-time. And it gets even more interesting if you have really massive and dense objects, like a pair of black holes orbiting each other, or something like that. Bottles of water are a little tame. Now, where you do have a pair of stars orbiting each other, so here's the pair of stars, gravitational wave goes away. The pair of stars loses energy. And when a pair of stars loses energy, they move closer together and go round faster, which means there's more gravitational radiation, which means they go around closer and faster, and there's more gravitational radiation, and they end up merging. And you end up with a waveform that looks something like the picture on the screen, where you can see the separate waves, but it gets faster and faster and faster, and stronger and stronger and stronger, until the ultimate merger. There may be a bit afterwards, but I won't go into that now. And the way you detect these is with an instrument called a Michelson interferometer. But it's very, very difficult, because the kind of movement you're looking for is of the order of 10 to the minus 18 of a meter. That's about 10 million millionth the width of a human hair. And they've done it. It's a phenomenally wonderful piece of work to be able to detect that amount of movement with a Michelson interferometer. Okay, the arms are kilometers long, and there's all sorts of wonderful devices to make it measurable, but they have done it. They have measured that kind of movement, and it's comparable in size to the size of an electron or a quark. This is the signal they get. Of course, it's a lot noisier than the ideal one I showed you. So along here is probably noise. And then you begin to see the waveform, and the wavelength is getting shorter and the amplitude's getting greater, and here's the merger. There are actually two signals here because they've got two detectors, with one in New Orleans, forgotten. Anyway, two in the US. Hanford's in Washington State, and Livingston's not very far from New Orleans. So that's a hugely important step that humankind has taken with the first real detection of these waves. It turns out that what they were looking at was the in-spiral of two big black holes, both of them weighing about 30 times the mass of the sun, in-spiraling. We didn't know that black holes of that mass were that common, as they presumably are, but it looks as if they are, so we have to revise. And what are the chances of getting two black holes that massive in a binary pair? Lots of questions about this. But this is a huge, huge development. And I'm watching with interest next Tuesday, around about midday, when from Sweden there'll be an announcement about this year's Physics Nobel Prize. We'll see. So my conclusion is that transient astronomy is very much coming of age. Do keep an eye on it because we are going to find lots of interesting, dramatic, unexplainable things. And the future, I think, is looking really very rosy. Thank you for your interest.